Hello students, welcome back. So in today's class that I am going to start with the fifth module, that is evaluating hypothesis, then instance based learning and reinforcement learning. So this module is also very important with respect to your examinations and in solving the real world problems, right? So first I am going to discuss evaluating hypothesis. So, empirically, when evaluating the accuracy of hypothesis is very fundamental to the machine learning. So, in this chapter, as I am going to present an introduction to the statistical methods for estimating the hypothesis accuracy, which will focus on three questions here. So, the first question is given the observed accuracy of a hypothesis over a limited sample of data, how well does this estimate its accuracy over the additional examples? And the second question is that given that one hypothesis outperforms the another over some sample of data, so how probable is it that this hypothesis is more accurate in general? And the third question is that when the data is limited, what is the best way to use this data to both learn a hypothesis and estimate its accuracy? Here, because of the limited samples of the data, it might misrepresent the general distribution of data. Estimating the true accuracy from such samples that can be misleading. So, the statistical methods, together with the assumptions about the underlying distribution of data, it will allow one to bound the difference between observed accuracy over the sample of available data and the true accuracy over the entire distribution of data. So this is all the fundamental about the evaluation part, that is evaluating the hypothesis. Now let us see the motivation part. So in many cases, it is important to evaluate the performance of the learned hypothesis as precisely as possible. One reason is simply to understand whether to use the hypothesis. For instance, when learning from a limited size database indicating the effectiveness of different medical treatments, so it is important to understand as precisely as possible the accuracy of learned hypothesis. The second reason is that evaluating hypothesis is an integral component of many learning methods. For example, in post-pruning decision trees, as I discussed this post-pruning decision tree. So in post-pruning decision trees, to avoid overfitting, we must evaluate the impact of possible pruning steps on the accuracy of the resulting decision tree. Therefore, it is important to understand the likely errors inherent in estimating the accuracy of the pruned and unpruned tree. Estimating the accuracy of a hypothesis is relatively straightforward when the data is plentiful. However, when we must learn a hypothesis and estimate its future accuracy given only a estimated set of data, there are two key difficulties that may arise. One is a bias in the estimate. Here, first, the observed accuracy of the learned hypothesis over the training examples is often a poor estimator of its accuracy over the future examples. Because the learned hypothesis was derived from these examples, so they will typically provide an optimistically biased estimate of hypothesis accuracy over the future examples. So this is especially likely when The learner considers a very rich hypothesis space, enabling it to overfit the training examples. So, to obtain an unbiased estimate of the future accuracy, we typically test the hypothesis on some set of test examples chosen independently of the training examples and the hypothesis. And the second key difficulty is that variance in the estimate. Here, even if the hypothesis accuracy is measured over an unbiased set of test examples independent of the training examples. So the measured accuracy can still vary from the true accuracy depending on the makeup of the particular set of test examples. Here, the smaller the set of test examples, greater is the expected variance. So in this chapter, as I will discuss the methods for evaluating the learned hypothesis, methods for comparing the accuracy of two hypotheses, and methods for comparing the accuracy of two learning algorithms when only limited data is available. Much of the discussion centers on basic principles from the statistics and the sampling theory through the chapter assumes there are no special background in statistics on the part of the reader. Here, the literature on the statistical test for the hypothesis is very large. So, this chapter provides an introductory overview that focuses only on the issues most directly relevant to the learning, evaluating, and comparing hypothesis. So, this is all about the motivation part. Then, the next very important concept is estimating the hypothesis accuracy. So, when evaluating a learned hypothesis, we are most often interested in estimating the accuracy with which it will classify the future instances. At the same time, we would like to know the probable error in this accuracy estimate. So, throughout this model, as we will consider the following setting for the learning problem, that is, there is some space of possible instances x over which various target functions may be defined. Here we assume that different instances in capital X may be encountered with different frequencies. Here a convenient way to model this is to assume there is some unknown probability distribution capital D that defines the probability of encountering each instance in capital X. So we can notice that capital D says nothing about whether X is a positive or a negative example. It only determines the probability that X will be encountered. Here, the learning task is to learn the target concept or the target function F by considering a space, that is hypothesis space capital H of possible hypothesis. So, training examples of the target function F are provided to the learner by a trainer who draws each instance independently according to the distribution capital D, and who is then forward the instance x along with its correct target value f of x to the learner. So to illustrate this, let us consider learning the target function, that is people who plan to purchase new material or new skills this year. So given a sample of training data collected by surveying the people as they arrive at the sky resort. So in this case, the instance space capital X is the space of all people who might be described by the attributes such as their age, occupation, and how many times they skied the last year. So the distribution capital D specifies for each person X the probability that X will be encountered as the next person arriving at the sky resort. Here the target function, that is f of x tends to 0 or 1, classifies each person according to whether they are not means whether or not they plan to purchase skies this year. So within this general setting, we are interested in two questions. So first question is, given a hypothesis H and a data sample containing n examples, draw at random according to the distribution D. So what is the best estimate of the accuracy of H over the future instance drawn from the same distribution? The second question is, what is the probable error in this accuracy estimate? So we are interested in these two questions. Yeah, it is within a general setting. So now I'll discuss about sample error and the true error. To answer these questions, we need to distinguish carefully between two notions of accuracy or equivalently error. So one is the error rate of hypothesis over the sample of data which is available. The other one is error rate of the hypothesis over the entire unknown distribution, capital D of examples. So we'll call these the sample error and the true error respectively. Here sample error of a hypothesis with respect to some sample S of instances drawn from X is the fraction of S that it misclassifies. So if you look into the definition, the sample error of hypothesis H with respect to the target function F and the data sample S it is represented as error S of H is equal to, that is equivalent to 1 by n summation delta f of x comma h of x, where x belongs to capital S. Here n is the number of examples in capital S and quantity delta of f of x comma h of x is 1 if f of x is not equal to h of x, otherwise it is 0. Next is the true error. True error of a hypothesis is the probability that it will misclassify a single randomly drawn instance from the distribution capital D. So if you look into its definition, here the true error which is denoted as error D of H. So the true error of hypothesis H with respect to target function F and the distribution D is the probability that H will misclassify an instance which is drawn at a random according to capital D. So it is given as true error, that is the error D of H is equivalent to PR f of x which is not equal to h of x, where small x belongs to capital D. Here the notation, that is PR x belongs to D, it denotes the probability which is taken over the instance distribution capital D. So what we usually wish to know is the true error, that is the error D of H of the hypothesis, because this is error means this is the error that we can expect when applying the hypothesis to the future examples. So all we can measure, however, is the sample error, that is the error S of H of the hypothesis for the data sample S that we happen to have in our hand. So the main question considered in this section is how good an estimate of error D of H is provided by error S of H, that is true error by sample error. So this is all about the sample error and the true error. Then the next important concept is confidence intervals for discrete valued hypothesis. Here we give an answer to the question, that is how good an estimate of error D of H is provided by error S of H. So for the case in which H is a discrete valued hypothesis, so more specifically, suppose if we wish to estimate the true error for some discrete valued hypothesis small h based on its observed sample error over a sample capital S, where sample S contains n examples drawn independent of one another and independent of H according to the probability distribution capital D. Here n is greater than or equal to 30. Then hypothesis H commits R errors over these n examples, that is error S of H is equal to R by n. So under these conditions, statistical theory allows us to make the following assertions or the following conclusions. First one, given no other information, the most probable value of error D of H is error S of H. The second one is, with approximately 95% probability, the true error, that is error D of H, lies in the interval, that is error S of H plus or minus 1.96 square root of error S of H into 1 minus error S of H whole divided by n. Now to illustrate this, suppose the data sample S contain n equal to 40 examples. Means to illustrate this, suppose consider the data sample S contains n equal to 40 examples and the hypothesis H commits R equal to 12 errors over this data. So in this case, the sample error, that is error S of H, is equal to 12 by 40, which is equal to 0.30, right? So given no other information, the best estimate of the true error, that is error D of H, is the observed sample error 0.30. However, we do not expect this to be a perfect estimate of the true error. So if we were to collect a second sample S dash containing 40 new randomly drawn examples, then we might expect the sample error, that is error S dash of H, to vary slightly from sample error, that is error S of H. So we expect a difference due to the random differences in the makeup of S and S dash. So in fact, if we repeated this experiment over and over, then each time drawing a new sample Si containing 40 new examples, we would find that for approximately 95% of these experiments, the calculated interval would contain the true error. So for this reason, we call this interval the 95% confidence interval estimate for error D of H. So in the current example, where R equal to 12 and N equal to 40 and 95% confidence interval is according to the above expression. So it is around 0.30 plus or minus 1.96 into 0.07, which is equal to 0.30 plus or minus 0.14. The above expression for 95% confidence interval can be generalized to any desired confidence level. The constant 1.96 is used in case that we desire a 95% confidence interval. A different constant, that is a Zn, which is used to calculate n percentage confidence interval. So the general expression for approximate n percentage confidence intervals for error D of H is error S of H plus or minus Zn square root of error S of H into 1 minus error S of H whole divided by n. Here you can see the different values of Zn for two-sided n percentage confidence intervals. So with respect to this formula, here constant Zn is chosen depending on the desired confidence level using the values of Zn given in this particular table. Hence, as we could calculate 95% confidence interval for error D of H to be 0.30 plus or minus 'I'll repeat. Hence, as we could calculate 95% confidence intervals for error d of h to be 0.30 plus or minus 1.96 into 0.07, where r equal to 12 and n equal to 40. So we can calculate 68% confidence intervals in this case to be 0.30 plus or minus 1.0 into 0.07. So we can note that it makes intuitions that the 68% confidence interval is smaller than 95% confidence interval, because we have reduced the probability with which we demand that error d of h fall into the interval. So with respect to this particular equation, that is error s of h plus or minus zn. So with respect to this equation, as it describes how to calculate the confidence intervals or the error bars for estimating error d of h that are based on error s of h. So in using this expression, it is important to keep in mind that this applies only to discrete valued hypothesis, that it assumes the sample S is drawn at random using the same distribution from which future data will be drawn, and that it assumes the data is independent of the hypothesis being tested. So we should also keep in mind that the expression provides only an approximate confidence interval. True, the approximation is quite good when sample contains at least 30 examples and error S of h is not too close to 0 or 1. So a more accurate rule of thumb is that the above approximation works well when n error S of h into 1 minus error S of h is greater than or equal to 5. So above is to summarize the procedure for calculating the confidence intervals for the discrete valued hypothesis. Then in the next class that I am going to discuss basics of sampling theory. So thank you.